In this video I'll be going through an example of the use of the RK4 method, which is the fourth order Runge Kutta method for solving a initial value problem. So I'm just to start off by reminding us what the method is. So the fourth order Runge Kutta method, it's a sort of single step method, as are all explicit Runge Kutta methods. So this is what we use to update our solution y. Okay, so we have these four stage values. So k1, as with all explicit methods, is just f of tn yn, and f of ty is your ODE function. K2 is slightly different, is f of tn plus a half h, yn plus 1/2 h times k1. K3 is f of tn plus a half h and yn plus a half h. K2. And finally we have the four stage value, which is f of tn plus h, yn plus h, k3. Okay, so this is our fourth order Runge Kutta method. So we have four stage values we need to calculate, and then once we've got the four stage values we can update the solution yn. Okay, so we're going to be using this to solve the IVP. This is from example, if I just remember what the example in the notes it's from. This is from example 2.5 in the notes. Yeah, so that's example 2.5. Right, so just the IVP we're going to solve is y dash is equal to sine squared t times y. The domain is between 0 and 5, and our initial value for y is going to be 1. So to start off with for step 1. Okay, so step 1 we need to calculate our stage values. So the first one's quite straightforward, is just our ODE function. So we've got sine squared of t0. So we start t0 initially. Should have just remind myself, t0 is 0, y0 is our initial value. So we've got sine squared 0 times y0, which is 1, which of course is 0. K2. So here we, instead of just t, we have t plus our step length 0.5 times a half. Oh, I've already put, I just put the half there. Okay, all that sine squared, and that's multiplied by, again, y0 plus a half h times k1. So y0 is 1 plus a half times h times k1, which was 0. Okay, and if you do those, we get 0.0612. K3 is quite similar to K2, except for we use K2 instead of K1. Just do that. So it's a half times h, and we got 1 plus 1/2 times h times whatever k1 was. And in this case this gives us 0.0613. And the last stage value is k4. So we have t1, t0 plus 1 times h, and we have yn plus 1 times h times our k3. Okay, so that's missing one close bracket. Okay, that is 0.2443. So once we've got the four stage values, we can calculate y1, which is y0 plus whatever our step length is divided by 2 multiplied by k1, which is 0, plus 2 k2 plus 2 k3 plus k4, and that gives us, what does it give us? It gives us 1.0411. That's correct, 4 decimal places. T1 is equal to our initial value of t, or t0, plus h, which was in this case 0.5. Oh yeah, I forgot to mention that at the beginning of the video. The step length we're using is 0.5. Okay, so this is the first step of the run cutter method. So what I'm going to do now is go on to do the second step. I'm not going to do all steps, that will be quite tedious. Okay, so for K1 again, so this is going to be, just to remind myself what our ODE function is. So it's f of ty, and that's equal to sine squared t times y. So we've got sine squared times t. Now this time t is 0.5. Actually, just to remind ourselves what from the previous slide or previous page what we had. Okay, and that's times by y, which we just calculated in the first step to be 1.0411. That gives us 0.2393. Okay, K2, so this is where we add a half times h to t, so 0.5 plus 1/2 times our h, just to remind ourselves, but we're using h as 0.5, and that's multiplied by y1, which was 1.0411 plus 1/2 times h times k1, which is 0.2393, and you do that calculation, it's 0.5393. Okay, continue on to K3. So very similar to K2, except for we have K2 instead of K1. So plus 1/2 times h, and this time we use our K2. And if we do that calculation, we have 0.0. Oh, sorry, we've got 0.0. We have a 0.6090. So you can see here I'm working all the time to 4 decimal places. And K4. So here we have t plus h, and we have y1 plus h times K3. And that works out at, what does it work out at? 1.1684. Okay, so once again we have our 4 stage values, so we can update our solution. So now we're going to calculate the second solution at the second step, which was equal to the solution at the first step plus h over 2 times K1 plus 2K2 plus 2K3 and plus K4. Yeah, and that works out, if you do the calculation, at 1.3498. And once again, we also have to, going ahead of myself there, we also have to calculate T2, which is simply equal to T1 plus H, and that equals 1.0. Okay, so that was 2 steps of the 4-forward Runge cutter method for solving this example IVP. I'm going to stop there. I'm not going to continue for the further 8 steps because it will get quite tedious. And you can see why we tend to use computer programs to perform all of these calculations for us.